Let's break down the paper trying to make a million token context something you run every single day. DeepSeek-V4 towards highly efficient million token context intelligence from DeepSeek-AI. It's really two models in one report, and by the end you'll be able to redraw its whole attention engine from memory and explain exactly why a novel's worth of context suddenly got cheap. A million tokens. That's a stack of context taller than most novels, handed to a model all at once. A whole code base, a year of chat history, a shelf of research papers, in a single prompt. The dream of an AI that reasons over all of it keeps smashing into the same wall. Attention gets catastrophically expensive as the context grows, so a million token prompt has always been a heroic, budget-torching one-off. DeepSeek-V4's entire mission is to knock that wall down, to make a million token context not a stunt, but something you run routinely. And here's the hook that should stop you. At that length, it does the job for a small fraction of the compute and memory its own predecessor needed. A longer context for less money. Let's see how. So why is long context so brutally expensive? Two reasons. First, attention is quadratic. Every token has to look at every other token, so the cost grows with the square of the length. Double the context, and you quadruple the work. At a million tokens, that's astronomical. Second, there's the KV cache, the model's running memory of every past token, its keys and values, kept around so future tokens can attend back to them. That cache grows linearly with length and just sits in GPU memory, gigabytes of it, doing nothing but remembering. Quadratic compute on one side, a bloating memory footprint on the other. Together, those two are exactly what has kept a million token context locked behind a wall of cost. The paper names the culprit directly. Before the mechanism, meet the two models, because DeepSeek-V4 is really a pair. There's V4 Pro, 1.6 trillion parameters, but only 49 billion active per token, the capability flagship. And V4 Flash, 284 billion parameters, just 13 billion active, the cost-efficient sibling. Both natively handle a full million token context. And here's the payoff up front, so you can decide this is worth your time. At a million tokens, V4 Pro runs each token for just 27% of the compute its predecessor version 3.2 needed, holding its memory in 10% of the KV cache. Flash pushes that even further, a tenth of the compute, 7% of the memory. That's the difference between a million token context being a stunt and being routine. Now, how do they get there? The whole trick starts with one realization. Stop treating all that memory as equally precious. The KV cache is where every past token is stored for attention to look at, so it's the natural pressure point. If you can shrink what's in there and prune what each new token actually reads, then every downstream cost, the compute, the memory bandwidth, the storage, falls at once. So the hero of this paper is an attention mechanism designed around one question. For a token being generated right now, how little of the past can it get away with looking at, and how compactly can that past be stored? DeepSeek-V4's answer comes in two flavors that work together. The first flavor is compressed sparse attention, CSA, and it does two things in sequence. Move 1 is compression. Instead of storing a key value entry for every single token, CSA takes every group of M tokens, M is 4 here, and squeezes them into one compressed entry, using learned weights that decide how much each token contributes, plus a learnable positional bias. So a million tokens worth of KV collapses to 250,000 compressed entries right off the bat. Picture a long ribbon of the past folding down, every 4 squares merging into one denser square. That alone is a 4 times cut in how much there is to store and to scan, and we haven't even started being selective yet. That's where Move 2 comes in. Don't even read all the compressed entries. This is the sparse part, DeepSeek Sparse Attention. A lightweight module they call the Lightning Indexer takes the current query and quickly scores it against every compressed block, a cheap relevance estimate computed with small low-rank projections and a ReLU. Then a top K selector keeps only the highest scoring blocks, 1,024 of them for Pro, 512 for Flash, and ignores the rest. Core attention only ever touches that selected handful, in an efficient multi-query form where each compressed entry serves as both key and value. The paper lays out both halves of the design in one sentence. The second flavor is heavily compressed attention, HCA, and it makes the opposite bet. CSA compressed groups of 4. HCA compresses groups of 128 tokens into a single entry. That's brutal compression. 1,000,000 tokens shrinks to just a few thousand entries, a tiny one-line abstract of each long stretch of the past. But here's the twist. Because there's now so little left, HCA doesn't bother being selective at all. And the real design is to use both, interleaved across the layers of the network. Some layers run CSA, keeping fine detail but only reading the most relevant chunks. Other layers run HCA, keeping only a heavily compressed gist but reading the entire past. Stack them, and information can flow both ways. A layer that needs sharp local detail has it, and a layer that needs the global sweep gets that too, cheaply. It's like a reader who on some passes schemes paragraph summaries of just the relevant chapters, and on others glances at a one-line abstract of the whole book, and by alternating, never loses either the detail or the big picture. That hybrid is what makes a genuine million-token context feasible in practice. Let's make it concrete with one query. Say the model is generating token 900,000, and it wants to attend to everything before it. In a CSA layer, those 900,000 past tokens are already stored as compressed entries. Divide by 4, so about 225,000 blocks. The Lightning indexer scores all of them, and the top K selector keeps just the best 1,024. To that, CSA adds the last 128 tokens uncompressed, a sliding window, because recent context deserves full detail, plus a learnable attention sink that lets the head dial its total attention down when nothing's especially relevant. Core attention runs over that small set, and a group projection folds the many heads back down cheaply. In an HCA layer, the same past is just 7,000 entries, and the query simply reads all of them. Either way, a query that used to face 1,000,000 keys now faces a few thousand. Add it all up, and the savings compound. Sparse selection means each query does a fraction of the multiply adds. Compression means the KV cache holds a fraction of the entries. Then they squeeze the storage further. The KV entries are kept in mixed precision. Full 16-bit only for the rotary position dimensions, 8-bit for the rest, which roughly halves the cache again, and the indexer runs in 4-bit. The net result at 1,000,000 tokens. The KV cache shrinks to around 2% of a standard attention baseline. Against their own already efficient version 3.2, that's compute 3.7 times lower for Pro and nearly 10 times lower for Flash, with a KV cache 9.5 to almost 14 times smaller. The wall didn't get climbed. It got demolished. The headline number, in their own words. Quick breather. If watching a lab refuse to pay full price for the obvious approach and demolish a wall everyone treated as fixed, is your kind of engineering, do the free thing that keeps this channel alive. Like, subscribe, and send this to the friend who still gets hit with context length exceeded. Right, back to the machine. Attention is the headline, but DeepSeek-V4 has 2 quieter upgrades worth understanding, and the first rebuilds the residual connection. Every deep network leans on residuals, the shortcut that lets each layer add its update on top of the input, so signal and gradient flow cleanly through dozens of layers. V4 replaces that single shortcut with hyperconnections. Instead of one stream running through the network, it widens the residual into several parallel streams. 4 of them here, with small learned matrices deciding how to mix between them at each layer. Think of a single-lane road upgraded to a 4-lane highway, with a learned rule for how traffic merges across the lanes. More lanes means richer information flow, but it also means more ways for things to go wrong. And that's the catch. Plain hyperconnections tend to blow up numerically when you stack a lot of them. The signal can get amplified layer after layer until training destabilizes. DeepSeek's fix is the clever bit, the M in MHC. They constrain the mixing matrix so it can never amplify. Specifically, they force it to be doubly stochastic. Every row and every column sums to 1, all entries non-negative, which they achieve with a few rounds of a classic procedure called the Sinkhorn-Knopp algorithm. A matrix like that has a mathematical guarantee. Its largest possible stretch factor is 1, so mixing between the lanes can redistribute information but never inflate it. The flow stays rich, and it stays bounded, even hundreds of layers deep. Freedom, but on a leash. The third upgrade swaps the optimizer, the rule that turns gradients into weight updates. For years, almost everyone has used Atom, which rescales each weight step individually. V4 switches to a newer optimizer called Muon, and the idea is geometric. Instead of tuning coordinates one at a time, Muon takes the whole update matrix and orthogonalizes it. Roughly, it straightens a lopsided, skewed step into a clean, balanced one where every direction gets a fair, unit-scale push. It does this with a short sequence of matrix iterations, cheap enough to run every step. In practice, that means faster convergence and steadier training at trillion-parameter scale, fewer steps to reach the same quality, which on a model trained over 30+ trillion tokens is an enormous amount of compute and money saved. Underneath all of this sits the engine DeepSeek carried over from V3, the mixture of experts design. Rather than every token flowing through one giant feed-forward network, each token is routed to just a handful of small expert networks, 6 of them, out of a couple hundred, plus one shared expert everyone uses. That's the secret behind those headline parameter counts. Pro holds 1.6 trillion parameters in total, but any single token only wakes up 49 billion of them. V4 tweaks a few knobs, a different activation for the routing scores, load balancing without an auxiliary loss, and a simple hash-based routing on the first few layers. But the core mixture of experts and multi-token prediction recipe is the proven one from V3. Efficiency by only ever activating the experts you actually need. Now the split that this report is really 2 papers about. Pro and Flash share the exact same architecture. They just dial it up or down. Pro runs 61 layers, selects 1,024 compressed blocks per query, and keeps 49 billion active parameters. Flash runs 43 layers, selects half as many blocks, and activates just 13 billion. So what do you give up going Flash? Mostly stored knowledge. Fewer parameters means less of the world memorized during pre-training, and Flash does trail Pro on knowledge-heavy benchmarks. But here's the interesting part. On many agent tasks, Flash keeps pace with Pro, and on reasoning it can nearly close the gap if you just let it think longer, spend more tokens at inference. It's a clean statement of the trade. Knowledge scales with parameters, but reasoning can be bought with test time compute. That covers the model. The other half of the story is how they finish it, the post-training. And it's a 2-stage idea worth knowing. Stage 1. Don't try to train a single model that's good at everything at once. Instead, train a separate specialist for each domain. One for math, one for coding, one for agentic tool use, one for instruction following. Each specialist starts from the base model, gets supervised fine-tuning on high-quality data for its field, and then reinforcement learning with GRPO, group relative policy optimization, against reward signals tailored to that domain. Think of it as sending 4 different students to grad school, each to become the best in the world at exactly one subject. The result is a set of narrow experts, each excellent, but none of them yet a single deployable model. Stage 2 is how you fuse those specialists back into one model, and they use on-policy distillation. The naive approach, just averaging the experts' weights together, tends to blur their skills and degrade performance. Instead, they pick one student model and have it learn to imitate all the teachers at once. The key phrase is on policy. The student generates its own responses, and for each one it's pulled toward whichever teacher is the relevant expert for that task, matching the teacher's full next token probability distribution, not just a single reward score. They minimize a reverse KL objective across more than 10 teacher models. So instead of merging weights, they merge behavior. The student practices on its own outputs and gets corrected by the right specialist every time. One unified model that inherited every expert's strengths. They describe the merge step precisely. A couple of post-training details round it out. Like recent frontier models, V4 has a reasoning dial with 3 settings: a fast non-thinking mode, a deliberate high-effort mode, and a max mode that pushes reasoning as far as it goes, all marked out with think tags in the output. For tasks that are hard to grade automatically, they use a generative reward model. The model acts as its own judge, and they train that judging ability with reinforcement learning right alongside the answering ability. And to make deployment cheap, they do 4-bit quantization-aware training. The model learns while already simulating the low-precision math it'll run at in production, so there's no accuracy cliff when you actually deploy it. Nothing bolted on after the fact. Efficiency is baked in from training. Does all this efficiency cost it intelligence? No, and this is the part that surprised me. In its maximum reasoning mode, V4 Pro sets a new state-of-the-art among open models. On SimpleQA, a tough factual knowledge test, it beats the next best open model by 20 full points. On competitive programming, it tops a Codeforces rating of 3,200 and leads on LiveCodeBench and the Apex coding shortlist. Best of everything measured, open or closed. And on the thing this whole architecture was built for, long context, it beats even Gemini 3.1 Pro on million-token retrieval and document question answering. It doesn't win everywhere. The report is candid that it trails the very best closed models by maybe 3 to 6 months. But it's genuinely in the conversation, while being the one that can afford to think across a million tokens. Their claim on where it lands. One result I don't want to skip, because it undercuts a lazy assumption. We tend to think bigger models are just better. But V4, Flash's base model, 284 billion parameters, beats the older version 3.2 base, which is more than twice its size, on the majority of benchmarks. A smaller model outperforming a much bigger one, because of better architecture, cleaner data, and the training improvements we just walked through. That's the whole thesis of this paper in miniature. Raw scale isn't the only lever, and often it isn't even the best one. FlashMax reaches frontier-tier reasoning at a fraction of the serving cost, which, for anyone actually deploying these things at 1 million tokens, is the number that matters most. It's not magic, and the report is refreshingly honest about the bill. First, the architecture is complex. It's frankly a pile of individually validated tricks bolted together, and the authors say as much, promising to distill it down to something more elegant next time. Second, 2 of their most important training stability fixes, one that decouples the router's updates, another that clamps activations, demonstrably work, but the authors admit they don't fully understand why, which is an unusually candid thing to put in a flagship report. Third, it still trails the closed frontier by a few months. And Flash, as we saw, trades away world knowledge for its speed. None of these sink the result, but 1 million token context that's cheap still isn't a free lunch. So let's rebuild the whole machine from memory. The problem: attention is quadratic and the KV cache bloats, so long context is ruinously expensive. The fix: in layers, compress the past, fold every few tokens into one summary entry. Then attend 2 ways. CSA reads only the top-scoring summaries, while HCA compresses even harder and reads all of the little that's left, and interleave both across the network. Widen the single residual into several constrained lanes for richer, stable flow. Orthogonalize every weight update with Muon for faster, steadier training. Route each token to just a few experts. Then post-train by raising domain specialists and distilling them all into one model. The payoff: frontier-level reasoning that keeps 1 million tokens in mind for a fraction of the cost. The one-line version, DeepSeek-V4 makes 1 million token context routine by compressing and pruning what attention has to remember, so it can think across a novel's worth of tokens at a small fraction of the compute and memory its predecessor needed. Here's why I think this paper matters beyond the benchmark table. There's a philosophy running through every DeepSeek release, and it's my favorite thing about them. Refuse to pay full price for the obvious approach. Full attention over 1 million tokens is the obvious approach, and it's ruinous. So instead of just buying more GPUs, they asked a sharper question: which parts of the past actually deserve a token's full attention? And the answer, it turns out, is not many. Most of a long context can be squeezed down to a summary, and most of those summaries can be skipped. That reframing is what turns 1 million token context from a stunt into infrastructure. the kind you can build routine long-horizon agents on, and maybe even models that keep learning online forever. So the thought I'll leave you with: if most of the past doesn't deserve a model's full attention, then how much of what we pay for, in every model, at every length, is just compute spin on information the model was never going to use? DeepSeek-V4's whole bet is that the answer is a lot. That's my read. Tell me yours. Until next time.